Okay.
I didn't find out that.
So here we go. Let's talk about a little bit of review. Oh, hey, Lauren.
I don't have it. I'm not doing it. Give me 0.
You're not doing it?
I forgot until yesterday and I was like, I said no way.
You want me to give you
Just
the
pay
zero?
him $5.
Give me a 0.
Yeah, I've heard Current and Resistance accepts $2 bills.
Give him a couple dollars. I'd rather you own it than pay for it.
No, yeah. Wait,
But when we do pay for it, we do own it.
If we already.
Yeah, you literally own it. Okay. Quick review here in this particular chapter. It has been a while. I know it has been a while.
Let's just not learn anymore.
What lesson did I even miss? That's what I.
I can check this. I don't know off the top of my head. Okay, so what have we talked about in this chapter? We talked about electrical potential energy, and we said it's due to location of a charge in an electric field.
I remember this. If it's opposite charges, the farther away they are, the more potential charges.
Yeah, so what we did, if you guys remember, we wrote electric field lines that were parallel, referring to like two electric plates or capacitors, okay? And we said if this is a positive plate, and I have a negative charge that is going this direction. Am I increasing or decreasing in potential energy?
Decreasing.
Decreasing. Okay? I'm allowing it to go in the direction that it wants to go. Okay? But if I were to be doing the same thing with a positive charge, okay, is it going to naturally go that direction? No, so I would have to do work to go that direction, which is going to increase and build up electrical potential energy stored up in that particular charge at that region. Okay? And that's what we said electrical potential energy was. Then I know we kind of got a little bit worked up about what potential difference is. It is the change in the electric potential. Okay? Yeah, so like, did I not say that before?
I just remember you saying that one time.
So yeah, basically what potential difference is your change in your electric potential energy. So, and we said potential difference was in what unit? Do you remember?
Big.
No, it was
Velocity. Volts.
Volts. Okay, when you have a battery, okay? When you have a battery that is a 12 volt versus a 6 volt battery, the main difference between them is you've got greater potential energy difference. You have greater charge separation, so that when you use it to power, you have more power running through its current. And we'll talk about how current and resistance and voltage work tomorrow, I believe, when we do Ohm's law.
I'm sure you heard of that.
Oh, it was a Ohm's law.
Yep. And that's going to be the law that we're going to use a bunch when we're doing electrical circuits next chapter, which is my favorite chapter. I'm gonna probably get our advanced chem this year.
Yeah, we better get
We are almost gonna get two more chapters further.
We better get there next time.
Kramer, when is our quiz for this chapter?
On Wednesday.
Not tomorrow.
I don't think we have one.
Yes.
Let me see. Yeah, no quiz for this chapter.
What the rate of this school's extracurriculars? I don't know if we're going to get through any chapters next year.
Amen to that.
I don't know. I'm gonna like make sure.
Never played anyway. Alright. Okay, also, then we talked about a capacitor.
Oh yeah, that was like.
Okay? And a capacitor is usually a metal plate that can store electric potential. Okay? Where you can cause charged particles to be moved onto a plate. So for example, if I had two plates, I could connect a battery to this, And what that would do would cause one plate to have an excess of negative charge, and the other plate to have an excess of positive charge. Excuse me. And that, when you're doing this, you're storing up potential energy, because do these negatives want to be by other negatives?
No.
No. So the more negatives you have here, the more positives that you have here, the more potential energy you have. So you have a large potential difference, or voltage. Okay? And we also said that the charges will stop moving when the potential difference on the plates are equal to the potential difference of the battery, because the battery isn't going to be able to charge more than its own voltage. Okay? And then we said you can take off the battery, and now you have these capacitors that you can use to plug in or apply to an appliance or something, and you can use that energy to produce work. Okay. We did some math.
We can get 101% on
No. I've never given over 100%.
That would have been enough for me to open up the class then.
I don't care if you do it in Spanish. Take your 115% to 160.
Actually, what? Spanish 4.
Oh, I'm sorry, I didn't know Spanish 4 was such a toy.
Actually, might as well know the way in
Yes.
class.
Did you read
Every time I walk by you guys in Spanish 4, you guys are talking.
One day. What's your guys' favorite?
So, let's move on to today's lesson.
What's today's lesson?
Current and resistance. It's right up there. Yeah.
This is the first time I've opened this book. You haven't even.
Hey, I know, we've been doing a lot of rooms, so we're going to go hard the rest of the year.
I just call him J-Bar.
Boy, I love your attitude today, Cole. It is great.
Wow, why do you say it like that now?
Great leadership.
I mean, this
Emma!
No reason to be
I'm not being grumpy.
Spanish.
J-R!
Okay, here we go. Did I turn it on? I hope I did.
Is it J-Bar? What do you say?
Sweet. All right. So, what do we?
I don't know what that is.
You don't have to be happy all the time. Just keep to yourself. Try to.
I still think Cole's depression comes from lack of sleep. Come to your bed last night.
I'm not. Stop saying I'm bad.
I went to bed. I went to
Let's start this.
I went to bed at 12:30.
Start the lesson.
Woke up without an alarm at 4. I went to bed at 9:30.
All right, electrical current. Okay, so current is the rate at which electrical charges pass through a given area. So, if electrical charges are moving really quickly through an area, it has high current. Okay? If charged particles are moving slowly, you have less current. Obviously, if you have more charged particles moving through an area quicker, you're probably going to be doing more work. Has more power. Okay, and there's a relationship that we're going to see tomorrow between the current and the voltage output. Okay? But before we do Ohm's law, we should probably figure out what even current is. The more electrons you can flow through, the more current you have, and the more work that can be done by the movement of charged particles. Okay? So we, just quickly, I'm sure you guys remember that Q is charge. T in this context is just the amount of time. And our new variable I, we've never used the variable I before, have we?
Of course we have.
Oh.
Because I stands for electric currents.
Well, we can't use E, because that's already used. Can't use C, because that's already used.
Technically, if you have used I then
Our Gross.
Alright, no problem. You guys are done. Here we go.
Chill, you're fun.
It's a visual
That's
concept.
the type of stuff I'm talking.
What did I do?
That was never, no, there was no.
I was trying to progress the lesson.
And I was already progressing the lesson. I didn't need your help.
Well, let's pay $5 and shut your
Yeah, that'll be $5 for it.
This is an awkward day. I don't know why this is doing 5
Kramer, what is
The
I
fact
then?
that I missed no school plays, but yet it takes forever. My mom asked me last night. She's like, Mom, fine.
Obviously.
Because that answer. He spazzed out.
I didn't say it like that, but I was just like,
I am
fine.
Here we go. I want to talk about one thing here called conventional current. Is that in your notes?
Yeah.
No, it's just the
Is it a number?
Can I write?
Well, that's in our notes.
Okay, I'm gonna write conventional current here.
Is it inequalities?
By the way, he also just said we're gonna have a but then
You
he
already
didn't
told me
get
that. You said, just trust God.
But we're not actually having.
Gerald, he's like, there's probably gonna be a quiz tomorrow, but don't worry, just trust God. I was like, okay,
That is
bye.
actually what he said. I heard that. But we're not. It's not.
Alright, I'm gonna talk about
Trusting God anymore.
3 cases.
Should this be under this?
No.
One's blood, but
Can you tell me which one's
one's
conventional?
One is water.
Okay? Because I know we're like, I think we've got a misconception that positive particles cannot move.
That's what he told us.
Yes. Quote, positive.
Protons cannot move out of the
This had a
nucleus.
positive
That doesn't mean that all positive particles can't move.
This had a positive charge.
He's a liar.
Okay? So, the first case we're most familiar with is just a conductor. Okay? That is going to be the motion
Of emotions.
of negative charges. Okay, the second case is going to be a particle accelerator. Hadron collider, yeah. Particle accelerator. What that is, this doesn't mean protons. This means a positively charged particle. Could be an ion, could be. We're not ripping protons out of the nucleus and shooting them at something. No, you cannot do that. So when I say motion of positive charges, I'm not saying motion of protons. Let's say I am moving a positively charged ion like sodium.
A positive charge weighs.
What did you
Are you telling me logically?
If this weight was positively charged,
Yes, I could make that positively charged, okay, via induction, right? We talked about induction, yes, last chapter, and then that was like 4 weeks ago, but we can make that positively charged, okay? Then can we put something, another positive charge or another negative charge up next to that and cause it to accelerate?
yes.
Absolutely. That would be an example of a positively charged object moving. Okay? Case 3.
Protons move.
Hey, don't worry, we can get 10% on the
Not on this one.
Is this Kramer's?
I really don't understand
I can't wait
what
till
you
they
guys say, how it affects me. You guys do what you believe is right.
Okay, I have a question.
I believe.
Say I were to buy it for someone else.
What'd you say?
I said, say I were to buy the pass for someone else, and they,
Why would you want to give them a crutch?
I don't know. I'm just curious. What do you-
Oh, reverse psychology. Give them a crutch so they focus more on the crutch and you can bypass them later. Because
Yeah.
they'll be hobbling around.
That's too many steps ahead.
No,
Before you jest.
Okay, so I was like, I'll buy it for you. You focus on that, but you buy it for me. I'll focus on that. It won't be wrong. Yeah, it won't be
More
wrong.
than.
It's only 1%.
Yeah,
Why do you
say
say that?
10% of a 10% grade.
Oh.
You say it all the time, getting I know.
Mine is only worth 10% of the grade. So, case 1, case 2, case 3, conventional current. Okay, this is going to be kind of tricky. It's just a way to, because if you have a positive particle and a negative particle, they're going to move differently, right? We just showed you an example in an electric field where a positively charged particle and a negatively charged particle would do different things within the same field. For example, if I have this field, okay, and here is a positively charged object that's creating that field. If I have a positive here and a negative here, are they going to move the same direction?
No.
No. Okay? So how are we going to figure out direction? How can we apply direction to a particular charged particle? What they do is they arbitrarily choose a standard. Okay? They say conventional current is specifically, okay, the flow of positive charges. So, if I am talking about
It's the electrical freeze. What, you know, AC?
Because grace doesn't matter.
kind of, yeah.
Oh.
Shoot, that's
Oh.
lower than I wanted it to be. No, it's just, guys, this isn't overly difficult to understand. I think you'll understand it as soon as I show you an example. So, a conductor is the motion of negatively charged particles. So if I have a negatively charged particle that goes that way, conventional current says that it goes the other way.
That makes sense.
Because if a negative goes that way, the positive is going to go the other way. And we're saying arbitrarily we're going to, in order to keep a standard so that we're not worried about, well, is the negative going this way or is the positive going this way, we're always going to focus on what the positive charged particle is going to do in that same situation.
That's a good direction.
What was that?
You'd rather look at the positive, not
Yeah.
focus on
I think the reason why they do that is because, do you remember how they defined electric field strength? And they said it was based on putting a positive test charge in an electric field. They didn't use a negative, did they? So they're trying to, I think, keep it on the same, the same idea and sticking with the positive here so that they're not flipping and doing negative in here, but then said positive for electric field.
Wait, that visual is actually. I don't.
So a negative moving this way is equivalent to the positive moving that way. Like if I have an electric field, right, in this situation, okay, the positive is going to move this way, but what's the negative? Okay.
I thought, the way you drew it down below, I thought there was like an object in between those two.
Oh, sorry.
So,
So,
like, this
and you're saying, yeah.
Like if there was an object in between.
Sorry, what I'm saying is, if a negative goes this way, sorry. Same thing here. If the negative goes this way, it'd be the same thing as saying a positive is going this way.
Okay, yeah, I was thinking of that.
Sorry, yeah. Maybe using this example will hopefully help clarify what I'm trying to say. Okay? Next one. Particle accelerator. If I have in a particle accelerator is the motion of positive charges, correct? Yeah, conductors, it's a motion of negative.
So it just both be.
Okay, so yeah, if a positive goes this way, conventional current says
The positive will also.
the positive will go that way.
So for the first one, why wouldn't would the other positive particle have an effect on the negative one?
Are these
They're not.
they're not part of the same situation. It's saying I want to give a direction, but I cannot do both at the same time because they do opposite things.
Okay.
And so we're saying conventional current is specifically in a situation, what will the positive do? So in a situation where the negative goes this way, what would a positive have done? The positive would have done opposite.
Conventional current's always the positive one?
Yes, and if you don't have that in your notes, write this in.
They can still take.
So conventional current is saying, if I have an electric or a negatively charged particle in a certain field, and that negatively charged particle goes left, if I were to place a positive charged particle in that same electric field, what would it do? It would go to the right. So if I said, what is the conventional current of a negative going to the right? You would all say?
A positive going to the left.
Yes.
What? So it's in
Well, this is an example of a conundrum. There are other examples where negatives will move. And I'm about, like, for example, in salt solutions, you have both a negative and a positive move, which I'll show you that in a second.
But then an accelerator is just fine.
Yeah. Okay, let's do salt solution. This refers to that. That's kind of a little off. Okay, in a salt solution, you have both. So like, for example, this would be a salt dissolving. You have a positively charged particle and a negatively charged particle, correct? So, let's say my positively charged particle moves to the right, and I have a negatively charged particle that moves to the left. What will be the conventional current for this? To the right. What will be the conventional current for this?
Right. Oh yeah, that's what I was. The way you write that, you know.
Oh, that's never
Conventional current is always what the motion of a positively charged particle does.
Okay.
It's just a standard, is all it is.
So then, are we going to be measuring for like how much it affects this? Like.
I'm not sure what you mean.
Like how are we going to be solving for like depending on how great the charge is, how much of 1%?
I don't think so. No. Honestly, this is more just a vocab than anything. Let me show it to you.
Wait, what is
It's based on what you define as conventional current. What did we define as conventional current? The flow of positive charges. So if this would be the opposite arrow, because field lines go towards the negative, right?
I just said.
Okay? Now listen. If I put a negative here, which way will it go?
It will go right.
What would conventional current go?
To the left.
To the left. Because the definition of conventional current is what a positive charge would do. So if a negative goes this way in this situation, a positive would go to the left. So let's say that I put a positive here.
To the left.
It's going to go to the left. What is conventional current going to say? It's going to go to the left.
Nice.
Because it is, by definition, the direction or the flow of which a positively charged particle will do. It's really not, I didn't mean to make it more complicated than it was. It's just a way of defining direction of flow of energy.
Conductor and salt solution is always positive, so
It's what?
that's kind of the same thing. It's a entire thing just made much more.
I was just giving examples of real life situations. Like conductor is an example, a salt solution is an example, a particle accelerator is a different type of example. I can give a variety of more examples. I was just trying to use that to arbitrarily define what dimensional
Now,
terms.
think about who's got like 5 minutes.
I said, the key
All right.
to success.
What is that?
So let's do this problem here.
What's A?
A is I.
Yeah.
What is K?
Yep, great. I haven't defined that yet. I'm glad you asked. A is the unit for current. It's called an ampere or amp.
Oh,
Ah.
That is fast.
Okay. Now I'm going to say the current of the light bulb is that. So A is ampere.
Wow, this isn't good. Easy.
It is. The math in this chapter is way easier than the math in last chapter.
Okay, so 1.6755.
Yeah,
You know, we can use this to cheese.
absolutely.
And we don't do that.
Although, when you're not using this, the cheat, the stuff on it is very, like, I just kind of messed around on there. It's
Wait,
very,
what is that? Ampere?
And.
How do you spell it? A-M-P.
Ampere.
There's no unit.
And it's like
1.67.
sphere at the end of it, so it's like
E-R-E, sorry. A with M, C.
Can we just say amp?
Okay.
I'm pretty sure it's spelled
We
that.
just say amp.
Nope, I did it.
I'm so glad there's no final.
There's
Wow.
no H there?
There was one.
So it's ampere, not
Did it make it sound like I said?
Yeah, I told them that.
MC, yeah.
So glad there's no final.
If it's total charge.
Sorry, Cole, by that time, you probably paid 50 bucks to get it.
Okay?
I see drivers.
Only you can control your.
Only you.
Only you.
What comes out was always within. How long does it take for the total charge of, okay, so if it says total charge, what do you think this is? I don't know why it doesn't have a unit.
1.67.
Go with Q.
I would
Yes, it is Coulomb.
Hold on.
I don't know why it isn't up there.
Well, it says a lot of times on my just said charge or something.
Really?
Yeah.
I
So
mean,
if it says total charge, it's
It's
the
been
same
too
thing,
long,
it's
I forget. What is cool?
Oh, that? Yeah, because that was final minus. Is the equation, why does it say change? Yeah, final
Yeah,
minus.
it's just change. That's
And
total.
like the equation.
oh, you could probably assume that all the charges are going to.
What's the charge on the last one?
1.6.
So I'm sure you guys can figure this out on your own.
No.
Two what?
The second one's a little
2
more
seconds.
tricky.
Huh? That second one's a little more difficult?
Yeah, let's do that.
1.9 times 10 to the 20.
Did everybody get 2 though? You don't want to go too fast.
Definitely.
I haven't done it yet.
What was the answer?
I got 2.
Just said 2 on a.
2 seconds.
It was oral.
So, this one, are we gonna even not, oh my god, this one?
Please no.
No, it's that number that
You
was.
should.
Electrons.
You're still solving for time. Do you multiply the electrons by the charge per electron?
Yes.
Okay, so then I got 30,040.
Wait, what's the charge in the electron?
And then 1.6 times 10 to the
Okay, so what information do we have?
We have how many? We have
I,
I.
which is 0.83 amps.
Yeah, they give us the power, but I don't think
I don't
we
think
need
any
it.
power.
You guys get 2. We can put it up there, but I don't think we need it.
You should probably plug it in.
Okay.
1.67.
How long does it take? Ooh, so it didn't tell us what the charge was, it just told us how many electrons we have.
Right, so then you multiply 1.9 times 7.2.
Okay? So this is how many electrons I have. I want to know what the charge of those electrons are so that I can figure out, what are we on for? How long? Time? Okay? So this would be E. We know that 1 E is equivalent to what for a charge? You guys remember?
1.66 times 10 to the negative 19.
Coulombs.
Or is it 23rd?
Yeah,
That's
yeah, so you get 3
No, let's say seconds.
That's 23rd.
Oh, you're saying, okay, yeah, 3040 was the answer to this. I thought you
Yeah.
were saying that was the final.
Oh,
Come
no.
on, Cole, you're slacking.
What's 6.022 times 10 to the negative 22nd?
It's not, that's, you're, oh my god, you're wrong, but you're wrong by one digit.
6.022 times 10 to the negative 23.
So this is the charge, okay, this is the charge of this many electrons. Okay, so 6.022 times 10 to the 23rd.
Yeah, you say, you think it's 22nd.
You said negative. It is negative. No, it's not.
I don't think it's negative.
I absolutely, I was thinking this, that'd be great. What? You didn't get this?
What?
19,
Because in my dream,
like,
I was in choir, which was.
okay, and then
And like you.
I is Q over T.
When I was making the oracles.
So now you have your Q and you have your I, you can find your T.
Okay.
Use the definition right now. It's 3.
Yes, it is a, I think if I remember right, it's a large number. What did you guys get for the time?
3,663.
Or approximately 1 hour.
That's a really lame light bulb. Is that, what's the
Well,
average wattage?
I don't know about, I don't know if you can, well,
That's a powerful light bulb.
It is?
Well, everyday light bulb. Usually everyday light bulbs are like 50 watts or 70 watts.
You said that the answers have to be in hours.
No, I just, so they need to be in seconds, it's fine. I was just,
You were just equaling it.
yeah, it's like 3600 seconds is an hour.
It's actually, if you had a suit that was all day,
I know it's not.
that's what you bring back.
I know. I just have been messed with a lot today.
Last
I've just been messed with a lot.